they form oxyacids, and then oxyacids, when they react with bases, and they form phosphates, right? So that is this story. कहाँ गया? Okay, share. Slide visible है ना? Slide is visible to you?
Yes, sir.
Yes, sir.
Visible.
Yes, sir.
Okay. So we'll start briefly with the phosphorus. As I said, it is a second member of the group 15 and is unique in its own way because of the entrance of the first D subshell, 3D shell, is involved in this period. And as we discussed last time, that as we move across third period from left to right, the nuclear charge progressively increases, and it has its consequences that the d orbital shrinks, atom also shrink, and d orbital, 3D orbital also becomes smaller and smaller as we go from left to right. And therefore, as we move from left to right, the effectiveness of the overlap, the d pi p pi overlap increases, and we will see that when you go to from 15 to 16 group, the d pi p pi bond becomes more and more strong and powerful. So what is, let's first say a bizarre story of the discovery of phosphorus, how this element was discovered. It was in Henning Brett, a German alchemist and physician, in 1669. He isolated phosphorus for the first time. And the surprising story that he was looking for a substance which could convert silver into gold. And for strange reasons, he chose human urine. And 50 to 60 buckets of urine were kept in a tub for long period till the urine started decomposing, and then this the dirty material was boiled down to form a paste, and the vapors were pushed, drawn into aqueous solution, into water, and which produced a white paste, waxy substance, and that glowed. There was glow in the dark, and if this waxy material was removed from water, it just bursts into flame, and there was no heat in this flame. This is a typical example of chemiluminescence, that there is a chemical reaction, phosphorus burns, reacts with air and forms oxide, but there is no heat released. In fact, the energy is converted into light, so it's a chemiluminescence. So Brandt called this product cold fire. So later, phosphorus, this element was called phosphorus, derived from a Greek word meaning light bearing. So this recipe was secretly purchased and passed among the select entrepreneurs, businessmen at that point in time, because this is a very strange element, and they thought this might be very useful for the public. And in 1937, this secret was sold after 68 years of the Brett's discovery. This secret was sold finally, officially, to the French Academy of Sciences, which made it public. They published just that you have a new element here, and the source of this element is human urine. So it was ultimately late in about 1 century after this discovery, in 1769, after complete 100 years, called Sheikh and Johann Gone found that phosphorus bones also contain the bones of the animals as well as human bones also contain phosphorus. But for a century, from 16 to 69 to 79, the only way to make the phosphorus was processing of human urine. It's a strange story that you could derive an element from human waste. There was so much, the people were so much obsessed with the phosphorus in 1800 when it was found that the phosphorus is useful in the sense that you could make safety matches that require phosphorus for ignition. And in England, there was demand for phosphorus so great that European battlefields were used for human remains. I mean, the wars were, waged to get the human remains, I mean, this human waste. Thankfully, now it is manufactured by a relatively normal procedure by heating phosphate rocks with sand and coke. So here is the reaction: calcium phosphate is a naturally occurring rock. It is heated with coke in presence of silica sand, and this generates calcium silicate plus carbon monoxide and phosphorus. So phosphorus, elemental phosphorus, generally it appears in three allotropes. One is white phosphorus, where there is red phosphorus, and then there is black phosphorus. White phosphorus is highly reactive. It reacts violently with air and moisture and generates flame. And therefore, to avoid this reaction, it's also highly poisonous. It is stored underwater to avoid the contact with air because it's highly reactive. When white phosphorus is heated in presence of sunlight, it gets converted into a much stable form, which is red phosphorus, which is generally used in matches nowadays. So then, if it is heated further under controlled condition under pressure, it gets converted into black phosphorus, which is an polymeric form. So white phosphorus and red phosphorus, they are tetraatomic. The P4 units, the phosphorus X is P4 units. So deep pi bonding, as I said, 3D orbital becomes more, effective in phosphorus, more smaller in phosphorus than in silicon, and therefore it forms much better bonds with the oxygen and nitrogen p orbitals. And then the result is that now we write regular PO bond, PO double bond, and PN double bond. And we have series of compounds, phosphazenes and phosphoric acid, oxyacids of phosphorus, oxides, which contain, which contain regular phosphorus, nitrogen, phosphorus, oxygen, multiple bonds. And also because of the d orbital availability of the d orbital, phosphorus can extend its valency beyond 4. It forms PF5, X3PO4, oxo acids, oxo anions, and other phosphazenes, a host of the other compounds which have the phosphorus atom involving the d orbital in bonding, and therefore extending its valency for forming 5 bonds. So usually phosphorus can be trivalent, it can be pentavalent, or sometimes it is also very unstable. +1 oxidation state is also there, but stable oxidation state is +5. So phosphorus forms +3 and +5 oxides. They should have been written as P2O3 and P2O5 by simple stoichiometric ratio is like this, but molecular formula is generally P4O6 and P4O10, dimer of this P2O3 and dimer of this P2O5. White phosphorus and red phosphorus, as I said, contain P4 units, and this is the tetrahedron. This geometry is tetrahedron. The 4 phosphorus atoms occupy the corners of a regular tetrahedron. And as we know, the tetrahedron has 6 edges and 4 triangular faces. So here there are the 6: 1 edge, 2, then 3 edge, then 4th, 5th, and 6th edge. So there are 6 edges in the tetrahedron, and phosphorus trioxide is that each edge has now oxygen as the bridging group on each edge. So there are 6 edges, Therefore, there will be 6 oxygen atoms, P4O6. So 1 oxygen, 2 oxygen, 3, 4, 5, and 6. So if you add another on each phosphorus, another oxygen formed linked with the regular sigma bond and then p pi d pi bond, you get P2O5. This is phosphorus pentoxide and this is phosphorus trioxide. So terminal, apart from the bridging oxygens, there is terminal oxygen also linked with the phosphorus by a regular sigma bond plus plus a p pi d pi bond. So this is phosphorus atoms 3d orbital and this is oxygen atoms p orbital, and this is sidewise overlap to generate the p pi d pi double bond pi bond. Phosphorus forms two series of oxoacids. These are phosphoric acids which contain plus 5 oxidation states, and they are good oxidizing agents. And phosphorus series, this is phosphoric series plus 5. Then we have phosphorus series plus 3 oxidation state, which contain which are not oxidizing agent, but rather they are reducing agent. They have pH bonds, and that pH bond is responsible for the reducing behavior. Phosphorus 4 is in all these oxyacids. Phosphorus is 4 coordinated and linked. The groups, the oxygen groups are directed towards the corner of a tetrahedron, and p pi d pi bond gives phosphorus oxygen double bond. POH group, the oxyacids are the acidic proton is not linked directly to the central atom, but it is rather linked to the central atom through an oxygen atom. Such type of acids are known as oxyacids. We have the example of sulfuric acid is another oxyacid, nitric acid is another example of oxyacid, because there also the acidic proton is not directly linked with the nitrogen, which is central atom in the nitric acid, or sulfur atom, which is central atom in the sulfuric acid, but it is rather linked through an oxygen atom. So such acids are known as oxyacids. So phosphoric acid and phosphorus acids also do not contain acidic. When you have hydrogen atom directly linked with phosphorus atom, that proton is not ionizable. That is not acidic, and in fact that proton is reducing agent, behavior responsible for the reducing behavior of the acids. So phosphorus in all these acids is 4 coordinated. P pi d pi bond gives phosphorus oxygen double bond. POH is the acidic proton, and pH is the reducing proton. The reducing behavior is because of the hydrogen. Whenever there is hydrogen atom linked directly with the phosphorus, that acid is having reducing character. So phosphate anion when heated, this undergoes condensation and or polymerizes, and a range of more complicated isopolyacids. Isopolyacids, when you add the acid and you heat it, there is dehydration or condensation, and you generate polymeric acids or polymeric salts. Such compounds are known as condensed phosphates or condensed phosphoric acids. So we have series of compounds where we can have the condensation, which involve the condensation of the monomeric acids generating the polymeric acids or their salts. So first is the phosphoric acids. The most common acid is orthophosphoric acid. This is phosphorus in the plus 5 oxidation state, and here it is phosphorus linked with the 4 groups, and these groups are directed towards the 4 corners of a regular tetrahedron, and there are 3 OH groups, and all of them are acidic groups, acidic protons, because they are linked to the phosphorus atom through oxygen atom. So this is tribasic acid. First proton is easily lost, second is lost with some difficulty, third is not lost. The third is very difficult to lose, but if you add the strong base, you can remove the third one also. So you have 3 series of salts possible. The sodium dihydrogen phosphate is an example in which one of the H positive has been removed and sodium has been incorporated there. This salt is slightly acidic in water, and when you have disodium hydrogen phosphate. This is known as dihydrogen sodium phosphate. This is disodium hydrogen phosphate. This is basic in water because once you dissolve this salt in water, it will undergo hydrolysis. It will generate phosphoric acid plus sodium hydroxide because base generated is very strong, and therefore the compound will undergo hydrolysis and will generate basic. This is slightly basic, and you have sodium phosphate when the third hydrogen has also been replaced by the sodium atom, sodium ion. Then you have this salt is perfectly basic in strong base in water. So sodium dihydrogen phosphate and dihydrogen sodium phosphate, they are when they are synthesized by treating this phosphoric acid with soda ash, that is sodium carbonate, weak base. When you add phosphoric acid, when you treat phosphoric acid with sodium hydroxide, a strong base, then you generate sodium phosphate, the last one. So it also, phosphoric acid also forms esters with alcohols. For example, when you treat it with ethanol, this is triethyl phosphate. The hydrogen atom is replaced by the ethyl group, and water is released as byproduct. So it forms ester, just as any acid will form ester. Try the phosphoric acid also forms esters with the alcohols. So, so detection. How this phosphate group is detected in any solid or liquid sample. If you have a solid sample and you want to detect whether this compound contains phosphate or not, if you have done the salt analysis in your earlier classes, in your undergraduate classes, then what you do, you take the salt and dissolve it in water, acidify with the nitric acid, then you add ammonium molybdate, and you get a yellow precipitate which is called ammonium heptamolybdate or ammonium phosphomolybdate, uh, ammonium 12 phosphomolybdate. And this compound has phosphate group at the center. This is phosphate, and this is double bond O, and O negative, O negative, and O negative. And to the O negative, you have this four molybdate groups, four here, and four here. So that is 12 molybdenum atoms. So overall the formula is, and then each molybdate has linked O negative here, and ammonium ion is there. So three ammonium ions. Take ammonium three times, then phosphorus at the center, molybdenum 12, and O40. This is the formula of ammonium phosphomolybdate, and this is immediately it forms a brilliant yellow color, dark yellow color, precipitate, and you say immediately that this compound, this salt, or this liquid contains phosphate. Suppose you have a water sample from a lake or from a water body, river, or from your from your water supply that you receive at your home, and you want to find out whether the phosphate from the agriculture runoff or from the domestic detergent sources or any other sources, if there is phosphate in this water or not, and to what extent it is there, that is the estimation that will be taken care of later on. But if you want to detect whether phosphate is there or not, so that is qualitative test, not quantitative but qualitative. You want to detect and find out whether the phosphate is there or not. So to take the sample, if it is already in the liquid state, you don't do anything. You just add nitric acid, little bit of nitric acid, acidify it, and then add ammonium molybdate. If you get yellow precipitate immediately, this compound, this water sample, this liquid sample contains phosphate. And if you don't get any yellow precipitate, then that sample does not contain phosphate. That is detection of the phosphate. And then estimation, you want to find out how much phosphate is there. So there is a technique which is known as gravimetric analysis. Gravimetric analysis, you precipitate a given analyte whose concentration you want to find out. You precipitate as an insoluble salt or insoluble complex, and then dry it, and or if it is stable, then dry it and weigh it as such. If it is not stable, then you ignite it, heat it, and convert it by heating, convert it into a stable compound which you can weigh, which does not change its composition with time, which is not hygroscopic, or it does not hydrolyze easily. And then you weigh its precipitate and then do the calculation by the using a conversion factor, proper conversion factor, and we will find out how much phosphate was there. So what we do, we prepare this solution of the sample. If the sample is, say your sample is your soil sample, agriculture. You want to find out how much phosphate is there in your land where you are cultivating some crop. So you take this clay sample, soil sample, and then first dissolve it into by using different treatments and make a solution of it, and then add magnesium chloride to it, and then add ammonium hydroxide to it. Then the phosphate gets precipitated as magnesium ammonium phosphate, which is white colored precipitate. You heat it in air, you get magnesium pyrophosphate, Mg2P2O7. This is known as magnesium pyrophosphate. This is stable compound, and you weigh it, and then you do the calculation by using a conversion factor. Say molecular weight of this compound is 400. So phosphate has molecular weight of 50. So we'll write 400 grams of magnesium pyrophosphate contains 50 grams of phosphate. 1 gram contains this much. Then you weigh it, this in the balance. Say you get zero point 0.5 grams, zero point 0.5 grams of the magnesium pyrophosphate. Multiply that 50 by 400 by that value, and you get the value of the phosphate. Then you write you have taken the soil sample, half of the gram of the 1 gram of the soil sample. 1 gram of the soil sample contains this much. 100 grams will contain this much. That will give you the percentage of the weight by weight percentage of the phosphate in the soil sample. So this is how the estimation is done for the detection as well as the qualitative and quantitative analysis of the phosphate. And surprisingly, the phosphates, the salts phosphates, most of the say alkali metals and alkaline earth metal, their phosphates are water soluble, 100% water soluble, except lithium and ammonium phosphate. These two compounds are not water soluble. Otherwise, but they also become soluble in acidic solutions when you add acid, etc. But most of the, say, particularly calcium phosphate, sodium phosphate, magnesium phosphate, they are 100% water soluble. For that reason, phosphates are also used as water softeners. They can, bind calcium and magnesium ions and remove hardness from water. They are used as water softeners. The only metals which form insoluble phosphates, which don't even dissolve in the acidic solution, are zirconium, titanium, and thorium. So if you want a sample, if you want a solution where phosphate should be completely removed, so you had removed your phosphate so much, but some traces of the phosphates were there which you want to remove. So just add zirconium nitrate. It will immediately precipitate the zirconium phosphate, and you can filter, and you are sure that even the traces of the phosphates have been removed from the solution. So because the zirconium, titanium, and hafnium, and the thorium, these four metals, they form phosphates which are 100% insoluble. They do not dissolve in water, even in the acidic water. So you can, if you want to remove the traces of phosphate in your sample, you just add the zirconium or thorium salt, zirconium nitrate or thorium nitrate. Then immediately the zirconium phosphate or thorium phosphate gets precipitated. You filter it, and your filtrate will be free from phosphate. Right. So now, when phosphoric acid or this orthophosphoric acid, when it is heated gently at 220 degrees Celsius, it undergoes condensation. One water molecule is removed, two molecules of the orthophosphoric acid react, and they form a dimer, which has four ionizable hydrogen atoms. Therefore, it is tetrabasic. So this is, its salt will be like this. And two negative here, another negative here, so four. This is known as pyrophosphate, P2O7 2 negative. So sodium, if you have sodium here, so it is Na4P2O7. That is the formula of sodium pyrophosphate, which was used earlier in earlier times as a water softener as it was a regular component of the detergents, because it could maintain the pH and make this solution detergent solution alkaline, and also therefore make the cleaning process more effective, because greases are the dirt and grease, they are more soluble in the alkaline medium, and also take care of the calcium and magnesium which form a scum with the soap or detergent, and do not allow the detergent to clean the do the cleaning process. So that these phosphates, sodium, this pyrophosphate, sodium pyrophosphate, was doing two things. It was maintaining the alkaline medium, which increases which effectiveness of the detergent increases, because greases and dirt are more soluble in the alkaline medium, and also it takes care of the calcium and magnesium, which will not allowing the froth to develop with the soap. Oh my God. Actually, yeah. Huh? ओके ओके बच्चों, लाइट चली गई है तो जब तक जनरेटर नहीं ऑन करते हो, तो अगर मैं ऑफ हो गया तो यू स्टे देयर, ओके?
Okay,
मेरी
sir.
आवाज
Okay, sir.
Okay, sir.
हाँ, मेरा कंप्यूटर बीप कर रहा है, तो कर देंगे शायद जनरेटर ऑन. So, uh, that is the sodium. That's the pyrophosphate, P2O74 negative tetrabasic acid, and also phosphoric acid is also known to form the cyclic polyphosphates. These are known as commonly they were earlier known as metaphosphates, but now this meta word has been discouraged. IUPAC, the International Council of Chemists, has now decided to use the cyclo word for these cyclic compounds. So cyclotriphosphate, cyclotetraphosphate, these words are now the authentic words, but still the old terminology survives. Some people are still using the metaphosphate terms. So this is the three phosphoric acid groups. When they condense in they form a cyclic compound also, tricyclophosphate. Like we can write the tetracyclophosphate. The formula of these tricyclophosphate, their repeating unit is PO3. That's why there is a phosphoric acid. We'll talk about that later on. That is known as metaphosphoric acid. The formula of that metaphosphoric acid is HPO3. And because in these compounds, this compound has formula of P3O9. If you count the number of oxygen atoms, every phosphorus has two terminals. So 3, 2 is 6, plus there are 3 bridging, 6 plus 3 is 9, and there are 3 phosphorus. So this is P3O9, 3 negative. So we can write it PO3, 3 times N minus N negative. So general formula for cyclic compound becomes PO3 N times N negative. So it is a tricyclic, so we'll write 3 here, 3 negative here. If it is tetra, we'll write PO3 4, 4 negative. Here it is PO3 4, 4 negative. 4 phosphorus, 12 oxygen atoms. So it is 4 negative. So because the repeating unit is same as the metaphosphoric acid, therefore they were called metaphosphates, cyclic compounds. But the exact word is, you have to write add this prefix of cyclo. Says that it's a cyclic compound. So this is cyclophosphate. Now, the polymeric, the phosphates can form a long polymeric chain, and there are sometimes the phosphates groups N can go up to 200. There are different compounds which have long chain and polymeric chain, and if it's a straight chain, you will have PO this type of dimer, then trimer, then tetramer, going on and on. So you will have PO3 at the center and PO2 negatives at the end. So the formula becomes polyphosphate becomes the PO4 two negative here. So this is N. N is how many repeat units are at the center, because in this middle of this, because in the middle of this series you will have one negative. So this is, say it is 4, so it is 4 plus 4, 4 negative. So if it is 1, so you will have 5 negative. So accordingly we can have, n can have any number. So phosphates are straight, can also form straight chain compounds. Their basicity will be n plus 4, H3PO4. Say this is dimer. This is what we know as pyrophosphate. Then it is trimer. Then we can have tetramer, so on and so forth. So this is dimer, this is tetramer, and you can go on and on. So the sequence, how this happens, this phosphate condensation, how it happens. Here we have the this phosphorus oxide, P4O10. Each phosphorus atom is linked with three other neighbors through bridging oxygen atoms, and then each phosphorus atom is linked with a terminal double bonded oxygen atom through d pi p pi bonding. So first I am breaking one of the phosphorus oxygen bridge by hydrolysis, HOH. So H goes to the one part, OH goes to the other. See, one bond breaks. So one edge breaks. And because there are 6 edges, I'm breaking first edge, and I get this P double bond OH and P double bond OH here. Then I break the second bridge, and I get this tetramer, this cyclic compound, 4 phosphorus atoms. This is tetra metaphosphoric acid. That's the common name, but now the name will be tetracyclophosphoric acid. And if you break this one again by hydrolysis, this one edge more, and this is not isolated in fact, but this is isolated. And if you break this one also, then you get this straight chain, 4 phosphoric tetra polyphosphoric acid, 4 phos. And if you break this again at the center by hydrolysis, you generate this pyrophosphoric acid, P2O7, H4P2O7. And if you break this further by hydrolysis, you get the phosphoric acid, orthophosphoric acid. Right. So the overall reaction is that P4O10 plus 6 times water gives you at 4 times H3PO3, 4 times phosphoric acid. But in between, you can get a cyclic compound also, then a tetramer also, then a dimer also, and then a monomer also. So successive hydrolysis takes place to generate this orthophosphoric acid, right? So many polyphosphates with chains up to 10 phosphate units have been isolated. So different polyphosphates with different number of this tetrahedra have been isolated up to 10. This is H3 orthophosphoric acid, then di or pyro, commonly known as pyrophosphoric acid, but correct name will be dipolyphosphoric acid, then tripolyphosphoric acid, then tetrapolyphosphoric acid, so on and so forth. So uh, the use is the sodium dihydrogen phosphate when mixed with sodium bicarbonate, it is called a packing powder. This was historically used, the mixture of the two. When they combine, they react to form the sodium phosphate and then the carbon dioxide, which levels, which makes the bread fluffy, and because of the emission of the carbon dioxide during the heating process. So this is known as baking powder. Dihydrogen sodium phosphate plus this is how the reaction takes place. This forms sodium pyrophosphate plus carbon dioxide and water. So sodium pyrophosphate was used as traditionally used as softener in soap powder, and sodium pyrophosphate was later on replaced by another compound, which is this triphosphoric acid, the derivative, the salt of this tripolyphosphoric acid, which has P3O10 in detergents. And now all the detergents, the solid detergents contain, the powder detergents contain, even liquid. There are some companies also market liquid detergents. They contain 20 to 45% of the this phosphoric this salt, triphosphoric acid, and some advanced countries have limited it to less than 20% because of the pollution, that phosphate causes. It makes the uncontrolled growth of plants in the water bodies, which makes oxygen supply limited to the aquatic life, and also leads to the fast eutrophication of the water bodies, the uncontrolled growth of the wheat, etc. And then water bodies generally, they have short lifetime. So many advanced countries are limiting the use of phosphates in the detergent powders. Soluble, why it is used as softener? Because it forms soluble complex with the calcium and magnesium. This process is known as sesquitration, and solution is alkaline, and that dissolves the grease. The long chain polyphosphates or linear metaphosphates, where N becomes large, then it forms a polyphosphate. When N is very large, more than 10, it is 20, 50, then we write the general formula, not the, PO4 10 times, it becomes the PO3 n times, because the this unit then becomes large. Say there are 400 or 200 phosphate units. Only the end one is PO3 or PO4. The central one, all repeating units are PO3. Then it is generally written as, when n is large, we write PO3 n times, n negative. Or when you have ring compound, they are generally written as PO3n and negative. So you can have long chains, they can be linear metaphosphates. One example of the long chain polyphosphate is Graham's salt. It's a long chain polyphosphate, wrongly called sodium. Initially, it was called sodium hexametaphosphate. There are 6 units of phosphate units, but it has a high molecular weight of the order of 12,000 to 18,000, and about 200 PO4 units. Therefore, it is not an hexametaphosphate, but it is having 200 phosphate units, and 10% of this 200 phosphate units, it contains these ring structures also, and cross-link chains also. So it's not a straight chain compound altogether. It is soluble in water and forms precipitates with lead and silver, but not with the calcium and magnesium. So commercial name of this compound is colgan. It is a water softener. It is commercially used for water softening. Uh, there are some companies, say, uh, this Aquaguard and other companies which install water softeners in the domestic as well as commercial buildings, which softens water and then supply the water to washrooms and to a kitchen, which is free from calcium and magnesium. They use this colgan as water softener. Water is passed through an ion exchanger which contains these compounds. So here is a reaction scheme how these polyphosphates are formed. This is sodium dihydrogen phosphate, a salt of the phosphoric acid. When it is heated to a temperature above 160 degrees, it forms sodium pyrophosphate, which is the salt of the sodium pyrophosphoric acid, disodium hydrogen P2O, disodium dihydrogen P2O7. So this heating degradation leads to dehydration, but 3 different products, when this compound is heated, it again undergoes dehydration, but 3 different products are formed depending upon the vapor pressure of water. So if you heat it in open air, different product is formed. If you heat it in closed system, different product is formed, right? So If the heating temperature is greater than 240 degrees, heated in air, that's open system, that is air is allowed to interact, you get a cyclic trimer, cyclic sodium trimetaphosphate. This compound, this one, cyclic metatriphosphate. This compound is formed by heating at 240 degrees, less than 240 degrees uh, 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 in air, open system. So sodium trimetaphosphate is formed. But if the temperature is about 300 degrees and system is closed, air is not allowed to interact, then you get polymer, a Muddler's high temperature salt, a polymeric salt which has long chain. And if you heat it at 200 to 300 degrees at higher temperature, then you get sodium Muddler's low temperature salt. If the temperature is higher, then you get high temperature salt. And if you keep the temperature lower, you again get the same polyphosphate, metaphosphate, but low temperature. This is having different composition. They are crystalline salts of phosphotetrahedral units with different, they differ in the length and the repeat unit. That's the difference, right? And when this cyclic compound is heated to 625 degrees Celsius, you form a liquid. This compound gets converted into monomer, breaks down from the trimer, cyclic compound breaks down and forms a liquid monomer, liquid melt. And when this liquid melt is rapidly, cooled, it forms another salt, a polymer, which is Graham's salt, which is a glass type. It is not a crystalline salt because it is all of a sudden cooled, and you get a glassy type of solid, which is known as Graham's salt. These are the names after the persons who synthesized them for the first time. This long chain polyphosphate gram salt, right? And then when it is heated above 550, you get coral salt, which is helical, which has helical chains, left helical and right helical chains. These are the salts which have same repeat units, but the length of the chains are different, and the repeat units are different, and their orientation is different, right? When you this liquid melt, when it is not cooled suddenly, but when it is heated to 580 to 590, it gets converted into this coral salt. And Graham salt also, when heated to more than 550, gets converted into helical, coral helical salt. And this coral salt also can be converted into Muddler's high temperature salt by 380 to 450 degrees heating, right? So then let us come to the metaphosphate, which is cyclic phosphate. This is a family of ring compounds. When you heat this phosphoric acid, you get HPO3, that is the general formula, and can be start from 3 because cycle cannot be formed with phosphate units less than 3. The ring has to be strain free. So we have the dimer will be like this, sharing two oxygen atoms, sharing, I will say, the edge of a tetrahedron, and that becomes full of strain, and therefore this compound is not formed at all. So cyclic compound starts from trimer. So this is tetramer. We have already discussed this. Then that was phosphoric acids, or I will stop here. We have only 5 minutes. If there are any questions, we'll do it next time. There are any questions? Hello, मेरी
No
आवाज आ
question,
रही
sir.
है? All of you
Yes,
are
sir.
there?
Yes, sir.
Okay. कोई सवाल है?
No, sir.
सब ठीक है?
सर
हाँ भाई,
सर
हाँ जी,
हमने कल पढ़ा था पी पाई और डी पाई बॉन्डिंग। उसके रिलेटेड था कि सर पी पाई डी पाई बॉन्डिंग हमेशा डेटी बॉन्ड ही बनेगा वहां पे क्या?
yes, because the d orbital of the p subshell is always empty, and
जैसे SO3 मॉलिक्यूल होता है, तो जब
हाँ
हम
हाँ
12th में पढ़ते थे तो हम वहां पे पढ़ते थे कि जो ऑक्सीजन है वहां पे 3 पी पाई डी पाई बॉन्ड्स बनते हैं, 2 पी पाई डी पाई बॉन्ड्स बनते हैं और एक वहां पे पाई
हाँ,
बॉन्ड बनता है।
यस यस, सल्फर डाइऑक्साइड जो न्यूट्रल मॉलिक्यूल है उसमें हो सकता है, बट ऑक्सी एसिड्स में जहां पे भी वो सल्फर अपना ये 6
हाँ,
कोऑर्डिनेशन में हो ना, ये टेट्राहेड्रॉन में, वहां पे डेटिव बॉन्ड ही होगा। क्योंकि अगर
ओके।
देखो, अगर आपके ऑक्सीजन के पास 2 लोन पेयर रहता है बॉन्ड के बनाने के बाद भी, तो
हम्म।
that is normal pi bond. If the lone pairs are not there, two lone pairs are not there, only one lone pair is there, obviously it is an dative bond. अगर
ठीक है।
ऑक्सीजन के पास 2 लोन पेयर बच जाते हैं बॉन्ड बनाने के बाद भी, पाई बॉन्ड बनाने के बाद भी, देन इट्स अ नॉर्मल, यू नो, इट्स नॉट अ डेटिव बॉन्ड। फिर उसने अपना लोन पेयर नहीं यूज किया।
ओके सर। सर जो पीएच रिड्यूस, मतलब आपने बताया ना आज की पी के साथ अगर एच जुड़ा होगा तो वो रिडक्शन कराएगा, सर क्या उसको थोड़ा सा एक्सप्लेन कर दीजिए फिर से, वो समझ नहीं
देखिए
आया।
देखिए, अगर जो एसिडिक प्रोटॉन होते हैं ना, वो हमेशा किसी इलेक्ट्रोनेगेटिव सब एटम के साथ जुड़े होने चाहिए, ताकि वो बॉन्ड जो है हाईली पोलर हो, और ऑक्सीजन जो इलेक्ट्रॉन पेयर है हाइड्रोजन के साथ जो बंधा हुआ है, उस पे कंट्रोल उस इलेक्ट्रोनेगेटिव एटम का हो, और वो उसको हमेशा लात मारने के लिए तैयार हो कि तुम जाओ यहाँ से बगैर इलेक्ट्रॉन के, देन दैट प्रोटॉन बिकम्स एसिडिक। आई विल गिव एन अनदर एग्जांपल कि जब कार्बन की इलेक्ट्रोनेगेटिविटी बहुत बढ़ जाती है, आप मीथेन से जाइए इथिलीन, और इथिलीन से जाइए एसिटिलीन, तो कार्बन की इलेक्ट्रोनेगेटिविटी प्रोग्रेसिवली बढ़ रही है। जो
हाँ एसपी आ जाएगा
एसिटिलीन
वहां पे।
कार्बन है, वो हमेशा इस ताक में होता है कि वो हाइड्रोजन को दफा करे एज एच पॉजिटिव।
ओके
क्यों?
सर।
क्योंकि सी एच बॉन्ड जो एसिटिलीन की होती है, उसमें कार्बन का बहुत कंट्रोल होता है, और वो हमेशा पुश करता है हाइड्रोजन को अपना इलेक्ट्रॉन यहीं छोड़ के चले जाओ, तो दैट बिकम्स द एसिडिक कैरेक्टर। तो इसी तरह ये जो फास्फोरस एटम है, अगर इसकी इलेक्ट्रोनेगेटिविटी इतनी ज्यादा है नहीं, लेकिन अगर इसके साथ एक इलेक्ट्रोनेगेटिव एटम है जुड़ा हुआ ऑक्सीजन जैसा, और ऑक्सीजन के आगे प्रोटॉन है, तो बिकॉज ऑक्सीजन एटम इज हाईली इलेक्ट्रोनेगेटिव, जो भी हाइड्रोजन थ्रू ऑक्सीजन जुड़ा होगा, दैट इज ionizable, that can be lost as H positive, whereas वो हाइड्रोजन एटम जो फास्फोरस के साथ डायरेक्ट कांटेक्ट में है, उस वहां पे इलेक्ट्रोनेगेटिविटी डिफरेंस इतना ज्यादा नहीं है, तो वो प्रोटॉन क्या नाम है, एसिडिक नहीं है, बल्कि वो रिड्यूसिंग, वो एज H नेगेटिव जा सकता है, और H
ओके
नेगेटिव जाएगा तो वो रिड्यूस करेगा किसी को, और फास्फोरस उस दौरान ऑक्सीडाइज हो जाएगा, क्योंकि वो फास्फोरस की लोअर ऑक्सीडेशन स्टेट में होगा, +3 में होगा, तो +5 में चला जाएगा फास्फोरस इन द प्रोसेस, और आपका जो दूसरा सब्सटेंस होगा वो रिड्यूस हो जाएगा।
ओके सर।
हेलो?
यस सर, समझ आ गया।
ओके, ठीक है। और कोई? हेलो? और कोई? ठीक है, फिर मैं लॉग आउट कर रहा हूं। थैंक यू।
Thank
Yes,
you.
sir. Thank you.
Thank you, sir.
हैव अ गुड डे।
Thank you, sir.